Welcome to this module. So, in this module, let us explore how analytics is actually being applied, not in theory but in practice across five of the most data rich industries in the world. So, for each sector, we will walk through real world case studies, the problem and the businesses face, the data and the analytic techniques, what they have applied, and the outcome achieved by them, and the key lessons learned. So, our five sectors are healthcare, retail, financial services, social media, and education. So each one has got its unique data challenges, regulatory contests, and potential impacts. So as we go through these common thread in every case, a value came not from having the data, but from asking the right question and applying the right analytical approach to answer it. So let us begin now the session. So before we dive into each case study, let me give you a 30-second orientation to the first five sectors that we are going to cover. So each sector row here shows you the core challenge, the main analytical tool which is being applied, and the headline business impacts. Those impact numbers are drawn from the real documented implementations. So few things on notice before we move on is that first, the scale of each market. So these are not just the applications, say like the healthcare analytics alone is a $45 million dollar global market. This social media analytics is being fueled by almost 5 million active users generating the data for every second. And second is the impact. Numbers are really they are real and they are very large, like fraud losses in it will cut down by 40 to 60%, and the students dropout is reduced by 18%, the retail basket size up to 22%. So analytics is not just delivering the marginal improvements, it is like delivering the structural change. And thirdly, you can notice that each sector has faced a lot of fundamental different type of analytical problems. Say takes healthcare. So healthcare is about the risk predictions on high stacks outcome. And retail is about the demand and personalization at scale. Finance is about anomaly detection in milliseconds. Like when you look into social media is about the unstructured language and the network effects, and education is about the earlier intervention before the students disengage. So every different problem, but we have got the same analytical mindset, right? Study is healthcare analytics. So healthcare is one of the most data rich industries on the planet, and historically one of the worst at using the data. A typical hospital generates terabyte of data daily across electronic health records, lab results, imaging systems, vital sign monitors, pharmacy records, and billing systems. So until recently, most of the data sat in silos. A doctor would see the patient's lab result, but not their pharmacy record from a different system. An administrator would see a bed occupancy, but not the downstream effect of the discharge delays. So that is changing fast. So we will look at three real world applications: hospital readmission prediction, diagnostic image analysis, and the operational efficiency in the emergency departments. So let us check out the first case study of the healthcare analytics. The Mount Sinai Health System in Newark faced a critical problem. The Centers for Medical Care and the Medicaid Services, CMS, was penalizing the hospitals financially for high 30-day readmission rates. For Mount Sinai, that penalty had reached millions of dollars annually. The analytical challenge is that we have to predict at the moment of discharge which patients are most likely to return within the 30 days before it happens. So the team has pulled 5 years of patient history across the EHR system, the pharmacy records, the vital signs, the lab results, and the social determinants of health, including whether a patient had a stable housing and reliable access to transport. So they engineered about some 285 features and they trained an XGBoost classifier. The critical challenge was a class imbalance. So only about 15% of the patients are readmitted. So a model that predicts no readmission for everyone achieved 85% accuracy, but it is useless, right? So they have used, in order to handle the class imbalance, they have used smooth oversampling to address this, and they achieved 87 percentage AUC compared to the 72 percentage baseline. So every patient receives a risk score at the discharge. So high-risk patients are flagged automatically to case a manager who calls within the 48 hours. And due to this, the result was that 25% reduction in readmission and about $4.8 million was being saved as a penalty payment annually. So here, the lesson that we learn out of this case study is that the model was only part of a solution. The human workflow, the case manager calling within 48 hours was equally critical. So this is the first case study that we can look into the 30-day readmission prediction model. And the healthcare analytics extends far beyond the readmission prediction. So let me walk you through 6 of the most impactful application currently in production. Say that let us take out the genomic risk um, stratification, which can combine the genetic data with the clinical history. So if a patient has got a BRCA1 mutation and the first degree related with breast cancer, the model can take out or make out a risk score for the targeted screening decades earlier than the standard protocols. And when we look into the medical imaging domain, that medical imaging AI is probably the most high profile application. The Google's DeepMind's system, it outperformed the radiologist on a mammogram analysis in a landmark nature study. So the technology is now in clinical use in multiple countries. And when we look at the population health management, it is all moving about from reactive to preventive care. So instead of waiting for a high-risk patients to turn up in the ED, the system identifies them in claim data and triggers a proactive outreach call. We can see the application in the healthcare sector mainly for the drug interaction prediction using the NLP on the clinical notes. It's not just a structured pharmacy data. The FDA Sentinel system, it can process almost over 300 million patient records to detect the adverse event signals. And next is about the operational flow optimization, which can treat the hospital like a complex system to be optimized. So predicting the 3D, the demand for the R allows the proactive staffing decision. And sepsis early warning is saving the lives directly by predicting the sepsis onset 6 hours before it becomes clinically obvious. Treatment can begin earlier. So, which is the single biggest determinant of a survival. So, these are some of the healthcare analytics and the key techniques and the applications where this data science is saving lives and cutting the cost. Case study is retail analytics. Retail has been transformed by data analytics more visibly than almost any other sector. Let us take Amazon. So Amazon built its entire competitive mode on data. Say recommendation engines, demand forecasting, dynamic pricing, warehouse robotics, all driven by analytics. But the application goes well beyond the e-commerce application. Say traditional brick and mortar retailers are using now analytics to complete the footfall analysis, the planogram optimization, the loyalty program modeling. So the core challenge in retail are what will customers buy, when, in what quantities, and how do we get it to them before a competitor does, right? So we are going to look into the retail analysis. Let us take out the case study as Walmart. Walmart is perhaps the most ambitious example of the retail analytics at scale. The old demand forecasting system used a simple 3-week rolling average of past sales that works when demand is stable, but it fails completely during a Black Friday, a hurricane warning, or when a competitor launches a major promotion. So the new system injects about 500 million data points daily, not just their own POS data, but external signals like say like local weather forecasts, school holidays, the sports uh, pictures, social media trend data showing what products are going viral, and even competitor pricing scrapped in the real time. So they use the LSTM neural network, a type of recurrent neural network, which is designed for the sequential and the time series data. So this model operates at SKU across the store level, 500 million individual combination of products and stores, each producing its own daily demand forecast. So the results when they started using this LSTM neural network was very amazing. Like there was 16% improvement in the forecast accuracy, 1.2 million billion dollars in annual inventory savings, and about 34% reduction in the perishable waste. So like which matters both financially and for sustainability targets, right? So the key lesson that we can learn from this case study is that almost 23% of the forecast improvements came from the external exogenous signals like weather, events, social trends. So if you only analyze your own internal data, you're missing almost a quarter of the predictive signal. And the session 3, we are going to deal about the financial analytics. So financial services may be a single most data intensive industry on the planet. The major banks like JP Morgan Chase, it processes billions of transactions every day across hundreds of countries in real time. Say these analytics in the finance operates across two horizons that would not be more different, like millisecond decisions and fraud detection and algorithmic tradings, and long horizon risk modeling that spans decades for mortgage portfolios and for pension funds. So the stack are also uniquely high. Fraud detection model that is slightly too sensitive, it can generate false positives that blocks the legitimate customers, and it can destroy the trust. So the model that is too lenient allows billions in losses. So let's look at how JP Morgan Chase built one of the world's most sophisticated fraud detection system. So JP Morgan Chase is the case study that we are going to deal with, and it is one of the world's largest bank by assets, and it processes around 10 billion transactions per year. So the scale of the fraud detection challenge is extraordinary, and the constraints are uniquely demanding. The decision to improve or decline a transaction must happen in under 2 milliseconds. So you cannot run a batch job, right? You cannot do a batch processing. So you cannot wait for a model to load. So every step in the pipeline, say a data retrieval, feature computation, or a model inference, a decision routing, must complete in a time it takes to blink our eyes, right? So their system uses four complementary techniques which works simultaneously. So let me tell you the four complementary techniques what JP Morgan use. First is the graph neural network, which models the relationship between the accounts, merchants, and the devices. The fraudster might conduct one suspicious transaction, but the network of accounts they have transacted with, which will light up across the dozens of flag patterns. And the real-time feature store, it pre-computes over 200 features about every account and transactions, including the velocity checks. So 5 transactions in 2 minutes is suspicious. And the location delta, like a card used in London and then in Tokyo 45 minutes later, is physically impossible, right? So the ensemble model approach, it reduces the single model blind spot risk. So different model architectures are good at different fraud patterns. And the unsupervised anomaly detection is critical for new fraud tactics like that do not yet being labeled training examples. The autoencoder says like this: a transaction is unlike anything that I've seen before, and it will automatically flag it to be as the fraudulent transaction or a fraudulent activity. So this is how the real world fraud detection across 10 billion annual transactions is being done by the help of the data analytics. In session 4, let us now deal with the social media analytics. So social media, as we see, it generates more unstructured data than any other sources on the planet. Over like 500 million tweets per day, 100 billion Instagram likes per day, 3.5 billion Facebook posts daily. And that is before we count TikTok, like LinkedIn, Reddit, and YouTube. So the analytical challenge here is different from every other sector we have covered. Like the data is almost entirely just text, image, and video, and it is unstructured by nature. So the traditional SQL and the spreadsheet tools are useless here. So you need NLP, you need computer vision, graph analytics, and the real-time streaming infrastructure to deal with the social media data. So we'll look at how the Netflix uses the social media analytics to guide the content commissioning decisions, a fascinating use case where the social data drives the billion-dollar investment choices. So the Netflix is one of the most sophisticated users of social media analytics in the world. The headline use case is using the social media to guide the content commissioning. So before commissioning a new series, Netflix analysts, they'll track the social conversation around the similar genres topics and talents, measuring the genuine organic interest versus the manufactured hype. So their BERT-based NLP model, it processes the billions of social posts every day, and it classifies them into sentiment categories, say positive, negative, mixed, and neural. So crucially, it also extracts the entity mentioned, which character, which actor, which plot element is driving the conversation. So the 24-hour early signal finding is the most commercially interesting insight here. Say, say that the social media data predicts the viewership trends 24 hours before internally viewing the data confirms them. So that is 24-hour head start on marketing decision, content promotion, as well as the PR response. So this social media analytics is playing a very important role here. And when we look into the trend velocity analysis, it is like 10,000 mentions, like growing 40% per hour is much a stronger signal than the 100,000 static mentions that are not growing. So the derivative is that the rate of change is more informative than the raw volume. So this Netflix, it tracks out the social sentiments on Disney Plus and the Prime Video launches in real time, identifying whether the competitor titles are disappointing the audience and where the Netflix can move fast to capture the display's attention. And even this social media analytics can be applied to the geographical sentiment heat maps for the hashtag lifecycle modeling and for competitive intelligence. And our final case study is on educational analytics. Education is perhaps the most personally meaningful sector that will cover. So here, the decisions analytics supports here where students are being analyzed. What is the risk of dropping out? Which teaching methods are working out for the students? How to allocate limited tutoring resources directly, which can affect the people's life and the life's outcome. So this all can be analyzed in the educational analytics. So the data available is extraordinarily rich. The modern learning management systems like Canvas, Moodle, and the Blackboard capture every click, every login, every assignment submissions, and every quiz attempt, and every forum post, right? So the ethical dimensions are also more sensitive here than in any other sector. Like when you are predicting whether a student will fail, you must be aware of the algorithmic bias, particularly like with respect to the socioeconomic background, race, and the disability status. So let us consider the case study of the Georgia State University, which alert early the student who is at the risk. So this Georgia State University is one of the most celebrated case studies in the educational analytics globally. And it is particularly like compelling because the GSU serves as a high proportion low income and first generation student population, the student who will be mostly benefited from the earlier intervention, right? So this university has implemented an early alert system that can monitor the students' engagement data from the LMS, and it flags that the risk students for a proactive advisor outreach. So this is one of the very interesting thing that this university has. So here the feature engineering is particularly, it is very thoughtful, like the strongest predictors are not what that you might expect. It is not the current grade, it is a grade trajectory, right? So a student whose grade is failing from B to C is at a much higher risk than a student who has consistently maintained a C grade. So a slope matters more than the level. This LMS login, what they have, the LMS login frequency before uh, what they have used, it is being tracked in this case study. So the LMS login frequency below 3 times per week is a 4 times stronger predictor for a disengagement than a poor grade at midterm, right? So the timeline here like shows the power of the patience and the iterative scaling. They started with a pilot of 300 students in 2012, and they refined the model. They expanded by 2022. The graduation rate of the Georgia State University has risen from 55 to 68%. That is 3,600 additional students were graduating every year. So this is something very interesting where data analytics play a very major role in the education sector. And now let's step back and look across all 5 case studies to identify the common pattern. So this comparison table shows that each sector uses different algorithms for different reasons. Like healthcare uses XGBoost because it handles the missing data and mixed feature types well. Medical data is always incomplete, right? So the finance uses Ensemble because no single model covers all the fraudulent pattern. The social media uses the BERT because it was designed specially for language understanding. But look at the lesson columns. 3 themes appear again and again. The first is that the last mile problem. In every single case study, the model creates value not only when the human acted on its output. The Georgia State model flagged at-risk students, but advisors had to email them. The Mount Zion's model, they predicted the readmission, but case managers had to call. A model sitting in a Jupyter notebook, outputting just the predictions nobody acts on, then it's worth nothing, right? So second is the data integration. So data integration is a real work. In every case study, 60 to 70% of the total project time was data engineering. It's not just model building. So joining the EHR system, like linking the POS data to weather, matching the social IDs to CRM records, the model is the easy part. And third is about the accuracy versus the explainability. The trade-off is real and it is context dependent. A doctor or an ethic board will reject a black box model that cannot explain why a patient was flagged, right? A fraudulent detection team at a bank cares about the AUC ROC, and it explains it later. So we should know the context before you choose a model. So let me bring together the key takeaways and the end with the ethical dimension, because it is non-negotiable. Like 5 takeaways from a 5 case study that I can give us. One is that every sector has a right question. Mount Sinai's right question was not what is wrong with this patient, it is which patient will return within 30 days. So finding that question is 50% of the work. And second is the external data consistency, which outperforms the internal data loop. So Walmart has proved this definitely, like weather, events, the social signals, they all add the first question to ask on that project is that what external data have we not yet considered? So that was a question in the second case study. In the third, Ensemble plus the human review, it beats the automation in a high stack decision. JP Morgan uses the Ensemble model for its prediction, and Georgia State, it flags a student but requires an advisor to actually act on the fly, right? And fourth is about the unstructured data hole, which holds a rich signal. The Netflix social listening, say the hospitals NLP on the clinical notes. So if you analyze only the structured data, the tabular data, you're missing a large part of the figure. And fifth is the earlier intervention, which can beat the retrospective reporting, like the analytics that saves a student, prevents a hospital's readmission, or blocks a fraudulent transaction. It happens before a bad outcome occurs, right? So not in a report. It also helps us to identify when before something goes worst. So on ethics, these are not optional considerations. So algorithmic bias is real and measurable, and the best data scientist thinks about the ethics at the feature engineering stage, not after deployment. So thank you. So happy to take up your questions.